Hey students, welcome back. It's time for the basics of electricity with volts, amps, and ohms. This is going to be some stuff you can write down, two equations you're going to learn in a lot of situations. But it won't take very long. So when it comes to electricity, I like to use the phrase about it. It's called VIRPE, V-I-R-P-E. It's kind of like what happens when you are about to vomit and you burp, right? The V stands for the volts, I stands for current, R resistance, P power, and E energy. Today we're going to look at the first three, V, I, and R. And this always is around the major idea, of circuits and electricity. Our common themes would be light bulbs. What happens if you have a bunch of light bulbs hooked up a certain way to a power supply? But that's what it's all about, the basics of circuits. So the first idea we're going to talk about today is electricity. You know it, you love it. If it goes out, we're screwed. But I don't like the word electricity. In fact, remember, we're going to use it like that again. Instead, we're going to use the word current. That is the official physics speak for electricity. Anytime you see the word current, you think electricity. But there's a little more detail to it. We're going to say officially current is the flow of positive charge, which you not like because of the fact that positive charges don't move, but Ben Franklin made a mistake. And so think of it as like electrons moving backwards. If electricity or current is flowing right, that means electrons are actually moving left. A lot easier to teach this way than simply change 200 years of like industrial blueprints. So, for our definition of electricity, it's the flow of positive charge. We're about to put an equation down there, which is I is charge over time. But that'll be in a little bit. Current also likes to flow. It has to flow from one point to another. We're going to say current flows from what's called high voltage to low voltage. You don't know what voltage is yet, but here we go. So if you have something that's high volts and something that's low volts, electricity will flow from high to low, which means the electrons flow from low to high. You might remember in class when I shocked you, you had to have been lower voltage than the thing shocking you. Otherwise, if you're the same voltage, nothing would flow. How about that? So if one thing's higher than you, electricity flows into you. If something's lower than you, electricity flows from you onto it. But instead of the word voltage, we're also going to use the word potential because we're going to change up all our words. I'm going to draw a battery right now. Battery has a positive end and negative end. All this means is a positive means high and negative means low voltage. Now I'm going to hook up a wire and hook up a light bulb between the wires. So this light bulb will turn it on because electricity is going to flow from high to low and it's going to go through the bulb. And life is good. That arrow I'm drawing is the flow. It's going to be an arrow. I'm laying one letter I next to it because that's the new letter for electricity. So you can see electricity is flowing from high to low. In the process, it's giving off light in a way. So I is the current. That's our new letter for it. It's measured in coulombs per second. We're going to call an amp. So current is coulombs over seconds, which is called amp for short. Now, even though electricity is flowing, current's flowing, electrons themselves, which are going from low to high, are not actually disappearing. We're not losing electrons, we're losing the energy that they carry in the form of light. So in this circuit, no electrons actually leave the circuit. They just move, and in doing so, they give off energy. The second thing is the word voltage, but as you saw from before, voltage is not a good word. Instead, I want to use the word potential, usually electric potential. For voltage, it's kind of weird, hard to describe. So I'm going to use this comic. There you go. You can see the three things here. We have a volt, an amp, and something new called an ohm. The amps is what's moving. Doesn't want to, but it will. And the volts is the push. You can imagine there's more volts on the left than the right because electricity flows from high to low. So a voltage is kind of a push. If there are two equal pushes, nothing would move. Two equal voltages, nothing moves. So you need a difference in push. You need a difference in voltage. And the ohms is what's kind of trying to resist it all. So when it comes to voltage, a couple things to keep in mind. First of all, think of it as like a push. Electricity goes from high to low. Therefore, the push is from high to low. And it's due to a difference. And that's why you see the phrase potential difference over and over and over again, which we're going to say is delta V. So if you hear like a 10-volt battery, what it really means is that it's a 10-volt difference. One side is 10 volts higher than the other. You have no idea what they actually are. It could be 100 volts to 90 volts or 10 volts to 0 volts. They both have the same effect. It's not the voltage that matters, it's the difference in voltage. So that's why I'm going to say the phrase delta V. Anytime you see V in an equation, it really refers to delta V. So delta V is what's called potential, aka voltage. It's measured in volts, and it really stands for the difference. A 120 volt outlet means there's a difference in 120 volts between one prong and the other prong. Now, finally, resistance, la résistance. Resistance is R, and it's a measure of what's called ohms, but we usually use the symbol of that. It's called omega. So if you see something that's 72 ohms, that's what it looks like. That means 72 ohms, but it's just a weird symbol for ohms. Now, when we think of resistance, it pretty much comes about from wires or other materials. Things that have resistance are like your toasters, your hair dryers, and light bulbs. All these things, what they do is they have resistance and turn energy into heat. That's the whole point. They're supposed to give off energy, heat. So some things you want high resistance for. For example, a hair dryer, you want to give off a lot of heat. Computers, not so much, you want low resistance. There are 4 things that the wires have or the materials have that affects their resistance. So these 4 you have to understand. The first thing that can affect the resistance of a wire or light bulb or toaster is actually the temperature it's at right now. I'm putting a star in there because it's an external factor. Usually the hotter something is, the more resistance it has. So a hot wire, it has way more resistance than a cold wire, which means it gives off more energy, which is why a hot light bulb gives off lots of energy. Number 2 is called the material, and I'm going to call this resistivity, which is the Greek letter rho. This resistivity is kind of like the material of itself. Metals have very low resistivity, and non-metals have really high resistivity. So hair, for example, have really high resistivity. I don't know why I'd electrocute hair, but I'm crazy like that. Next up is length. The length of the wire makes a big difference. The longer the wire, the more resistance it has, which means if you have a very long charging cable, it actually takes longer to charge it because there's more resistance. And finally, the 4th thing that affects it for a wire or for a light bulb is the thickness of the wire or the thing itself. Usually the thicker the wire, the less resistance, the less resistance it has. So you want a thicker wire. Now the resistance of something depends on its resistivity times length over area, which makes sense. The bigger the area, the less resistance. And temperature is not a factor in here because it's an external factor. So that's usually the 3 things you can control. A long, thin wire is very slow charging compared to a short, thick one. Finally, now let's talk about symbols. We're going to be drawing a lot of circuits here. When it comes to voltage potential, we refer to them as 2 lines, one longer than the other. The longer one's the longer one's high, the lower one's lower, whatever. Next up, resistance is usually a squiggly line, and for a wire with no resistance, just a straight line. So I'm going to draw a basic circuit, the battery hooking up to a light bulb. The current is also a line, you'll see. So there's the battery, there's the light bulb, and there's the other wires connected to it. So if this is 20 volts, and that's 10 ohms, that's how I'd write a circuit like that. That shows a single light bulb hooked up, and there's the current flowing from high to low, even though electrons are going from low to high. You can actually get really more complicated stuff. We're going to do soon this, where there's 3 light bulbs, or maybe 3 other devices hooked up in this way. You can see in this circuit, there's one battery powering a couple things, or one outlet powering a couple things. Electricity flows, splits into 2 unequal parts probably, and it comes back together. This is our circuit diagram. Finally, let's talk about the relationship between these 3. You saw that comic from before with the volts pushing, the current flowing, and the resistance resisting. This is called Ohm's law. Now, Ohm's law deals with what's called ohmic situations. These are situations where the resistance of the object does not change. I'm putting a star next to it because that means that the temperature can't actually change. Remember, there are 4 things that affect resistance. So if something is 50 ohms and the voltage is 10, it'll be 50 ohms whether it's 10 volts or 100 volt difference, or whether it's 1 amp or release tiny milliamps. The resistance should be the same for it to be considered ohmic. So if things heat up, like light bulbs normally, they're not ohmic. That means that you can't actually cut away parts of the wire, that kind of stuff. So things like light bulbs, which change temperature, are non-ohmic, or for things that change resistance. You could have a resistor that changes resistance with a switch. Ohm's law is a simple mathematical relationship on your formula sheet. It is the difference in voltages I times R, where R is always fixed, no matter what happens to V and I. So if you increase the voltage, by definition, the current must increase because resistance doesn't change. You push more, you get more flow. And with that, that's kind of the idea behind this. It's how voltage relates to current. So if you were to draw a graph of voltage and current, as you push more, current goes up more. Solving for V over I, you get R, which we said before is fixed. So you should end up with a straight line. That shows that you have the same voltage to current ratio. If it's non-ohmic, however, like for example, it gets hotter, V over I, which is R, is going to change. That can't be a straight line. As a light bulb gets hotter, resistance goes up, which means that it has less flow. So you could think about it as having an asymptote. There's a current it can never actually go beyond because it gets hotter and hotter. So we get this curved behavior. That is a non-ohmic situation. V over I is not a straight line. And with that, my friends, that is the basics and introduction of it. You can see right here, a gigantic push gets you a little bit gain in current. It is not the same resistance over time.